Tonight, we're going to talk about something you interact with every single second of your life, but almost certainly do not understand. Mass. You feel it when you stand up. You fight against it when you push a heavy object. It's the reason you're stuck to the ground right now. But here's the thing nobody tells you. Most of the mass in your body doesn't come from what you think it does. In fact, about 99% of the mass of everything you've ever touched has nothing to do with the Higgs field. Nothing. And yet, without the Higgs field, you wouldn't exist. Not a single atom could form. The universe would be unrecognizable. What's really going on is stranger and more beautiful than almost anyone realizes. Before we get into this, if you find these kinds of deep explanations fascinating, a quick like or subscribe genuinely helps this channel keep going. It's a small thing on your end, but it makes a real difference for me. Now, make yourself comfortable. Let's begin. Let's start with something you already know. Mass. You experience it every moment of your life. When you pick up a bowling ball, it resists you. It's heavy. It doesn't want to move. When you try to push a car that's run out of fuel, you feel the enormous effort it takes to get it rolling. That resistance, that stubbornness that objects have when you try to change their motion, that's mass. You've understood this intuitively since you were a child, even if you didn't have a word for it. A basketball is easier to throw than a boulder. A bicycle is easier to push than a truck. A coin slides easily across a table when you flick it. A brick does not. You know this. It's built into your experience of the world from the very first time you tried to lift something heavy as a toddler. Mass is one of the most basic properties of matter. It determines how much force you need to accelerate something. It determines how strongly gravity pulls on an object. It determines how much energy is locked inside matter itself. Your weight, the number you see when you stand on a bathroom scale, that's a direct consequence of your mass being pulled on by Earth's gravity. The reason you don't float off into space is that you have mass and Earth has mass, and gravity connects the two. Mass is so fundamental to your experience of reality that you probably take it for granted. Of course, things have mass. Of course, objects resist being pushed. Of course, a rock is heavier than a feather. These seem like obvious truths about the universe. Things just are heavy or light. That's how the world works. You don't question it any more than you question why the sky is above you or why time moves forward. Mass just is. But here's where things start to get strange. If you ask a physicist what mass actually is, where it comes from, why particles have the specific masses they do, the answer turns out to be one of the deepest and most surprising stories in all of science. Because for most of the 20th century, physicists had no idea why anything had mass at all. They could measure it. They could calculate with it. They could use it in equations, but they couldn't explain where it came from. Mass was a mystery hiding in plain sight. To understand why mass was such a puzzle, you need to understand a little about how physicists describe the universe. And that means talking about the standard model of particle physics. Now, I know the phrase standard model sounds dry and technical, like something from a textbook you'd rather not read. But trust me, the standard model is one of the most extraordinary achievements in the history of human thought. It is our best description of how the universe works at its most fundamental level. It describes everything that makes up the world around you, every atom in your body, every photon of light entering your eyes, every force that holds matter together, every radioactive decay happening inside distant stars. The standard model took decades to build. Hundreds of physicists contributed to it across multiple countries and generations. Thousands of experiments tested its predictions. And it works. It works with a precision that is almost absurd. It is arguably the most successful scientific theory ever constructed by human beings. The Standard Model describes the universe in terms of fundamental particles and fundamental forces. Let's start with the particles. According to the Standard Model, everything in the universe, every object, every substance, every piece of matter you've ever encountered is built from a surprisingly small number of building blocks. There are 12 fundamental particles of matter divided into two families, 6 quarks and 6 leptons. The quarks have whimsical names: up, down, charm, strange, top, and bottom. These names don't mean anything physical. Physicists just needed labels, and these stuck. Of the 6 quarks, only 2 matter for everyday life: the up quark and the down quark. These 2 quarks combine in groups of 3 to form protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up quark. Protons and neutrons make up the nucleus of every atom, and atoms make up everything you see and touch and experience. The other 4 quarks, charm, strange, top, and bottom, are heavier and unstable. They existed in the early universe and can be created in particle accelerators today, but they decay almost instantly into lighter particles. They don't stick around long enough to form stable matter. They're like exotic relatives you've never met. They exist, they're part of the family, but they don't come to dinner. Then there are the leptons. The most familiar lepton is the electron. Electrons orbit atomic nuclei and are responsible for chemistry, for the bonds that hold molecules together, for the electrical signals in your brain, for the light emitted by your phone screen. Without electrons, there would be no chemistry, no biology, no life, no technology. The electron is arguably the most important particle in your daily life. The other leptons include the muon and the tau, which are heavier, unstable versions of the electron. The muon is about 207 times heavier than the electron, and the tau is about 3,470 times heavier. Both decay rapidly into lighter particles. There are also 3 types of neutrinos, one associated with each of the charged leptons. Neutrinos are ghostly particles that barely interact with anything. They have incredibly tiny masses, so small that for decades physicists thought they might be completely massless. Trillions of neutrinos pass through your body every second without touching a single atom. They stream out of the sun in unimaginable numbers. About 65 billion of them pass through every square centimeter of your skin every single second. And yet, they do essentially nothing. They pass through the entire Earth as though it weren't there. They're so elusive that for decades, physicists weren't sure they existed at all. The neutrino was first proposed theoretically by Wolfgang Pauli in 1930, but it wasn't detected experimentally until 1956. So that's the matter side of the Standard Model. 12 fundamental particles, 6 quarks and 6 leptons. From these 12 particles, you can build everything. Every star, every planet, every ocean, every living thing. All of it comes from combinations of these 12 building blocks. That's elegant. That's beautiful. The universe, in all its complexity, is built from just 12 types of fundamental particles. But particles alone don't do anything. They just sit there. To make the universe work, to make things happen, you need forces. Forces are what allow particles to interact with each other. And the Standard Model describes 3 fundamental forces. The first is electromagnetism. This is the force that holds atoms together, that allows chemistry to happen, that produces light, that makes magnets work, that carries electrical signals through wires and through your nervous system. Electromagnetism is carried by photons, particles of light. When two electrons repel each other, they're exchanging photons. When an atom absorbs light, it's absorbing a photon. Electromagnetism is everywhere in your daily life. The second force is the strong nuclear force, sometimes just called the strong force. This is the force that holds quarks together inside protons and neutrons. And it's the force that holds protons and neutrons together inside atomic nuclei. Without the strong force, protons and neutrons couldn't exist. Atomic nuclei would fly apart instantly. Every atom heavier than hydrogen would be impossible. The strong force is incredibly powerful, roughly 100 times stronger than electromagnetism at nuclear distances, but it only acts over very short ranges, about the size of an atomic nucleus, roughly 1 femtometer, which is 1/4,000,000th of a meter. Beyond that range, its effects vanish almost completely. The strong force is carried by particles called gluons, named because they glue quarks together. There are 8 types of gluons, and unlike photons, gluons themselves carry the charge of the strong force, which makes the strong force behave in very unusual ways. We'll come back to the strong force later because it plays a role in the mass story that will genuinely surprise you. The third force is the weak nuclear force. This force is responsible for certain types of radioactive decay. It's what allows a neutron to transform into a proton, releasing an electron and a neutrino in the process. The weak force is carried by 3 particles called the W+ boson, the W- boson, and the Z boson. These are heavy particles, which is part of why the weak force is weak. It only operates over extremely short distances, even shorter than the strong force. There's also gravity, of course, but the standard model doesn't include gravity. Gravity is described by Einstein's general theory of relativity, and incorporating it into the standard model is one of the great unsolved problems in physics. For the purposes of particle physics, gravity is so weak compared to the other forces that it can be safely ignored. The gravitational attraction between 2 protons, for example, is about 10 to the power of 36 times weaker than the electromagnetic repulsion between them. That's a 1 followed by 36 zeros times weaker. Gravity matters for planets and stars and galaxies, but at the scale of individual particles, it's essentially irrelevant. So the standard model gives us 12 matter particles and 3 forces, carried by force-carrying particles, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. Together, these particles and forces describe virtually everything we observe in the physical world. The standard model has been tested thousands of times in experiments around the world. Its predictions have been confirmed to extraordinary precision. In some cases, the agreement between theory and experiment is better than 1 part in 10 billion. That's like predicting the distance from New York to Los Angeles, and being accurate to within the width of a human hair. No other theory in the history of science has been tested this thoroughly and passed every test. But here's the problem. The beautiful, elegant, stunningly accurate standard model had a deep flaw, a crack running through its foundation. And that crack was mass. You see, when physicists wrote down the mathematical equations that describe the standard model, something awkward happened. The equations only worked. The mathematics only remained consistent. If all the fundamental particles were massless, Every single one of them. The photon, the electron, the quarks, the W and Z bosons, all of them. The math demanded that they have zero mass. Now, photons and gluons being massless is fine. Photons actually are massless. That's why they travel at the speed of light. Gluons are also massless. So far, so good. But electrons, quarks, the W and Z bosons, these particles definitely have mass. We've measured their masses with great precision. The electron has a mass of about 9.1 times 10 to the power of negative 31 kilograms. That's incredibly tiny, but it's not zero. The top quark, the heaviest fundamental particle we know of, has a mass roughly equivalent to an atom of gold. The W and Z bosons are roughly 80 to 100 times heavier than a proton. These are not massless particles, so the physicists had a crisis. Their theory, the Standard Model, worked beautifully in every other respect. Its predictions matched experiments to extraordinary precision, but the mathematics demanded massless particles, and reality clearly contained massive particles. Something was wrong, or rather something was missing. You might think the obvious solution would be simple. Just add mass to the equations by hand. Just put in the masses of the particles as numbers, and move on. But that's exactly what you cannot do. And the reason is something called gauge symmetry. Gauge symmetry is one of those concepts that sounds intimidating but is actually quite elegant. At its core, gauge symmetry is a mathematical property that the equations of the Standard Model must have in order for the theory to be consistent. It's not optional, it's not a preference, it's not something physicists chose because it looks nice, it's an absolute requirement. Without gauge symmetry, the Standard Model makes predictions that are mathematically nonsensical. You get infinities where you should get finite numbers. You get probabilities greater than 100%, which is physically impossible. A probability of 120% doesn't mean anything. It's like saying there's a more than certain chance of something happening. The whole framework collapses into meaningless gibberish. Think of it like this. Imagine you're building a bridge. The bridge needs to be built with certain structural principles, the laws of engineering and physics, or it will collapse under its own weight. You can't just add weight to the bridge wherever you want. You need to add it in a way that's consistent with the structure's design. If you add weight in the wrong place or in the wrong way, the bridge falls down. It doesn't matter how beautiful the bridge looks or how well the rest of it was built. One structural flaw in the wrong place and the whole thing comes crashing down. Gauge symmetry is like the structural principle of the Standard Model. It's what holds the entire theoretical framework together. It ensures that the theory produces sensible predictions, that the probabilities add up correctly, that the mathematics doesn't generate nonsensical infinities. And when physicists tried to add mass terms directly to the equations, those mass terms violated gauge symmetry. The theoretical bridge collapsed. The math stopped working. You got nonsensical predictions. Infinities everywhere. Probabilities that exceeded 100%. The theory became useless. This was deeply frustrating. Physicists had this magnificent theory that described almost everything about the fundamental particles and forces, and they couldn't explain the most basic property of matter. It was like having a perfect blueprint for a house that somehow didn't include doors. You had the walls, the roof, the windows, the foundation, everything except a way to get inside. Something essential was missing. The problem was particularly severe for the W and Z bosons, the carriers of the weak nuclear force. These particles are heavy, very heavy by particle physics standards. The W boson has a mass of about 80.4 billion electron volts, and the Z boson has a mass of about 91.2 billion electron volts. For comparison, a proton has a mass of about 938 million electron volts. The W and Z bosons are nearly 100 times heavier than a proton. This mass is what makes the weak force weak. Because the W and Z bosons are so heavy, they can only exist for incredibly brief moments before decaying. They can only mediate interactions over extremely short distances, roughly 1,000th the diameter of a proton. If the W and Z bosons were massless, like the photon, the weak force would be just as strong as electromagnetism and would act over infinite distances. The universe would be completely different. Atoms as we know them couldn't exist. The nuclear reactions that power the sun would proceed at entirely different rates. Stars would burn differently. Chemistry wouldn't work the way it does. The periodic table of elements would look nothing like what we know. You wouldn't be here. Nobody would be here. The entire structure of matter as we know it depends on the W and Z bosons having their specific masses. So the masses of the W and Z bosons aren't just numbers in a table somewhere. They're essential to the character of the weak force. They're essential to the universe being the way it is. They're essential to our existence. And the Standard Model, for all its brilliance, for all its precision, for all its staggering success in describing virtually everything else, couldn't explain where those masses came from. It couldn't explain why the W and Z bosons were heavy while the photon was massless. It couldn't explain why different particles had different masses at all. The situation in the early 1960s was something like this. Physicists had developed quantum field theory, a mathematical framework for describing particles and forces. They'd used this framework to build the Standard Model. The model was incredibly successful in many respects. Quantum electrodynamics, the part of the Standard Model that describes electromagnetism, made predictions that agreed with experiments to astonishing precision. The strong force was being understood through a theory called quantum chromodynamics. The weak force was being described with increasing accuracy, but the mass problem loomed over everything. Particles had mass. The theory said they shouldn't, and you couldn't just force mass into the equations without breaking everything else. Several physicists working independently in the 1960s arrived at a radical idea. What if mass isn't an intrinsic property of particles at all? What if it's not built into them from the start? What if particles are born massless, exactly as the equations demand, but then acquire mass through some other mechanism? What if there's something out there, something filling all of space like an invisible ocean, that gives particles their mass through interaction? What if mass isn't something a particle has, but something a particle gets? This was a revolutionary concept. Instead of the particle having mass built in, the particle would gain mass by moving through a field that permeates the entire universe. Different particles would interact with this field to different degrees. Particles that interact strongly with the field would have large masses. Particles that interact weakly would have small masses. And particles that don't interact with the field at all, like photons, would remain massless. In 1964, 3 separate groups of physicists published papers proposing versions of this idea. Robert Brout and François Englert in Belgium published their paper in August of that year. Peter Higgs in Edinburgh published his paper in October. And Gerald Guralnik, Carl Hagen, and Tom Kibble in London published their paper in November. All three groups arrived at essentially the same conclusion through different mathematical approaches. The idea is now most commonly associated with Peter Higgs, partly because Higgs was the one who explicitly pointed out that the mechanism would produce a new particle, a boson, that could be detected experimentally. This particle would later become known as the Higgs boson. But the key idea wasn't really about the particle. The key idea was about the field. A new kind of quantum field that fills all of space and interacts with other particles in a way that gives them mass. This field is what we now call the Higgs field, and the mechanism by which it gives mass to particles is called the Higgs mechanism, or more properly, the Brute-Englert-Higgs mechanism. The Higgs mechanism resolved the contradiction at the heart of the Standard Model. It allowed the equations to remain gauge-symmetric, preserving the mathematical consistency of the theory, while still producing massive particles. The gauge symmetry isn't destroyed. Instead, it's hidden. Physicists call this spontaneous symmetry breaking, and it's one of the most beautiful and powerful ideas in modern physics. The concept of spontaneous symmetry breaking isn't unique to particle physics. You can see it in everyday situations. Imagine a ball sitting on top of a perfectly symmetrical hill. The hill looks the same in every direction. The ball is at the peak. This situation has perfect symmetry. But the ball can't stay there. It's unstable. The slightest push, the tiniest disturbance, will send it rolling down one side or another. Once it rolls down, the symmetry is broken. The ball ends up at the bottom on one particular side, even though the hill itself is still perfectly symmetrical. The underlying law hasn't changed. The hill is still symmetric, but the actual state of the ball has broken that symmetry. The ball chose a direction, even though no direction was special. Here's another way to picture it. Imagine you're at a round dinner table with other guests, and there are water glasses placed between every pair of place settings. Before anyone sits down, the table is symmetric. Every seat is the same. But the moment the first person picks up a glass on their right, the symmetry breaks. Now everyone has to pick up the glass on their right or the glass on their left, following the pattern. The underlying table is still symmetric, but the actual situation has broken that symmetry. The Higgs field does something similar, but on a cosmic scale. The laws of physics, the equations of the Standard Model, have a certain symmetry. But the Higgs field, like the ball on the hill, has settled into a state that breaks that symmetry. It didn't have to pick any particular direction, but it did. And that breaking of symmetry is what gives particles mass. This was an extraordinary proposal. It meant that mass, one of the most fundamental properties of matter, isn't really fundamental at all. It's acquired. It's emergent. It comes from the interaction between particles and a field that fills the entire universe. The universe isn't full of intrinsically heavy particles trudging through empty space. It's full of intrinsically massless particles interacting with a field that gives some of them resistance to acceleration, the property we call mass. But in 1964, this was just theory. An elegant mathematical solution to a real problem, but still unproven. There was no direct evidence that the Higgs field existed. No one had ever detected the Higgs boson. No experiment had ever produced a signal that could confirm this idea. For all anyone knew, the real explanation might be something completely different. Nature doesn't care about elegant mathematics. Nature does what it does. And sometimes the most beautiful theories turn out to be wrong. What followed was one of the longest and most expensive searches in the history of science. Physicists knew roughly what they were looking for. The theory predicted a new particle, the Higgs boson, which would be the observable signature of the Higgs field. Finding this particle would confirm that the field existed. It would validate decades of theoretical work. It would complete the Standard Model. But the theory didn't predict the exact mass of the Higgs boson. It could be anywhere within a wide range of energies, and producing it would require enormous amounts of energy concentrated into an incredibly tiny space, which meant building bigger and more powerful particle accelerators than anything the world had ever seen. The search would take nearly 50 years. It would cost billions of dollars. It would require the construction of the most complex machine in human history. And the outcome was never guaranteed. The Higgs boson might not exist. The theory might be wrong. Physicists might spend decades and billions of dollars looking for something that simply isn't there. But here's what you need to understand about why this mattered so much. This wasn't just about finding a new particle. This was about understanding the origin of mass itself. Mass is what gives substance to the universe. Without mass, particles would fly around at the speed of light. They couldn't bind together, atoms couldn't form, chemistry couldn't happen, stars couldn't ignite, planets couldn't coalesce, life couldn't evolve, you couldn't exist. The question of where mass comes from is really the question of why anything in the universe has substance at all. Why there's something rather than nothing. Why the universe isn't just a soup of massless particles racing around at light speed, never interacting, never forming structures, never becoming anything. That's why physicists spent 50 years and billions of dollars on this search. Because the answer to where does mass come from is really the answer to why does the universe look the way it does? Why is there structure? Why are there atoms and molecules and stars and planets and people? Why isn't the universe just a featureless blur of massless particles racing around at light speed, never clumping together, never forming anything? Mass is what makes structure possible. Mass is what makes the universe interesting. And in the early 1960s, physicists had a theory. An elegant, beautiful, mathematically consistent theory that resolved one of the deepest problems in physics. But a theory without evidence is just a story. A compelling story. A plausible story. A story that resolves real contradictions, but still a story. What they needed was proof. Hard, experimental, undeniable proof. And getting that proof would require an effort unlike anything the scientific community had ever attempted. It would require machines of staggering complexity, collaboration spanning entire continents, and a level of precision that pushed the boundaries of what humans are capable of. The search for the Higgs boson wasn't just physics. It was one of the greatest engineering challenges in human history. And the outcome would either confirm our understanding of why mass exists or force us to start over from scratch. But before we get to that story, we need to understand the Higgs field itself more deeply, because the mechanism by which this invisible field gives particles mass is genuinely one of the strangest and most beautiful ideas in physics. And grasping it, really grasping it, changes how you see everything around you. Every object, every atom, every piece of matter in the universe looks different once you understand what the Higgs field is actually doing. The chair you're sitting on, the air you're breathing, the body you inhabit, all of it is intimately connected to this invisible field that fills every cubic centimeter of space. And what it does, how it works, is something most people have never been told properly. So what exactly is the Higgs field? You've probably heard the name before. Maybe in a news headline. Maybe in a documentary. Maybe someone mentioned it at a party and you nodded along pretending to understand. But what is it really? Not the simplified version. Not the dumbed down metaphor. What is the Higgs field actually doing? In our universe, let's start with the word field. In physics, a field is something that has a value at every point in space. That's it. That's the definition. A field is a quantity that exists everywhere. You already know about fields even if you don't realize it. Temperature is a field. At every point in this room, there's a temperature. It might be slightly warmer near the heater and slightly cooler near the window, but there's a temperature value everywhere. You could, in principle, measure the temperature at every single point in the room and create a map. That map would be a temperature field. Gravity is a field. At every point near Earth's surface, there's a gravitational pull pointing downward toward the center of the planet. It's slightly stronger at sea level than on top of a mountain. It's slightly stronger at the poles than at the equator, because the Earth isn't a perfect sphere and because the equator is slightly farther from Earth's center. But there's a gravitational value everywhere. You move through this gravitational field every day. It's pulling on you right now. It's the reason your feet stay on the ground. You don't see it. You can't touch it. You can't smell it or taste it. But it's there, filling all of space around the Earth. And it affects everything with mass that enters it. The electromagnetic field is another example. At every point in space, there's an electric field value and a magnetic field value. When you turn on a light, the light bulb creates electromagnetic waves that ripple through the electromagnetic field. Those ripples are what we call light. The electromagnetic field fills all of space. It's everywhere. When a radio station broadcasts a signal, it's creating ripples in the electromagnetic field. Those ripples travel outward at the speed of light, and when they reach your radio's antenna, the antenna responds to the ripple and converts it back into sound. The field was there the whole time. The broadcast just created a disturbance in it. Now, here's the key difference between the Higgs field and these other fields. Most fields have a value of 0 in their lowest energy state. Think about the electromagnetic field in empty space, far from any charges or magnets. Its value is 0. There are no electric or magnetic fields present. The field exists, it's there, it's ready to be disturbed, but its resting value, its ground state, is 0. If there are no charges and no magnets, and no light waves passing through, the electromagnetic field just sits there at 0, doing nothing. The Higgs field is different, fundamentally different. The Higgs field has a non-zero value everywhere in the universe, even in the emptiest, most remote corner of the universe, far from any star or galaxy or atom, in the deepest void between superclusters where almost nothing exists. The Higgs field is not 0. It has a specific non-zero value. Physicists call this the vacuum expectation value, and it's approximately 246 billion electron volts. That number might not mean much to you, but what matters is that it's not 0. The Higgs field is always on. It's always there. It's always doing something. There is no place in the universe where the Higgs field is turned off. You cannot escape it. You cannot shield yourself from it. It permeates every cubic centimeter of space, from the interior of atoms to the vast voids between galaxy clusters. It fills the entire universe like an invisible ocean with no surface and no bottom. This is what makes the Higgs field so unusual and so important. Most fields are zero unless something disturbs them. The Higgs field is never zero. It's perpetually switched on. And it's this constant, ever-present, non-zero value that gives certain fundamental particles their mass. But how? How does a field that fills space give particles mass? This is where we need a good analogy, and I want to be careful here because every analogy for the Higgs field has limitations. No analogy is perfect, but some are useful for building intuition. So let me give you a few and then explain what's really going on. Imagine a room full of people at a party. The room is packed. Now imagine a celebrity walks in. As the celebrity tries to cross the room, people crowd around them, slow them down, make it harder for them to move. The celebrity acquires a kind of resistance to movement because of their interaction with the crowd. Someone who isn't famous could walk through the same room more easily because fewer people would cluster around them. And someone completely unknown could slip through barely noticed, encountering almost no resistance at all. In this analogy, the room full of people is the Higgs field. The celebrity is a particle that interacts strongly with the field, acquiring a large mass. The unknown person is a particle that interacts weakly with the field, acquiring a small mass. And someone who is somehow completely invisible, who doesn't interact with the crowd at all, passes through freely. That's a massless particle like the photon. This analogy captures something important. Mass in the Higgs mechanism isn't about the particle being made of heavier stuff. It's about how strongly the particle interacts with the Higgs field. A particle with a large mass isn't bigger or denser in some physical sense. It just couples more strongly to the Higgs field. The field resists its acceleration more. It's harder to get it moving and harder to stop it once it is moving. That resistance to changes in motion is exactly what we experience as mass. Specifically, it's what physicists call inertial mass, the property that determines how much a particle resists acceleration when a force is applied. Here's another analogy that captures a different aspect. Imagine you're trying to walk through a swimming pool filled with thick honey. Every step is slow and difficult. The honey resists your movement. You feel heavy. You feel sluggish. Every motion requires enormous effort. Now imagine your friend is trying to walk through the same pool, but they're smaller and more streamlined. They have an easier time. They slip through the honey more quickly because their shape interacts with it less. And now imagine a tiny fish, sleek and narrow, that can dart through the honey with almost no resistance at all. The honey is the Higgs field. You, your friend, and the fish represent particles with different coupling strengths to the field. The stronger the coupling, the more resistance, the more inertial mass. But I want to be clear about the limitations of these analogies. The Higgs field isn't really like a crowd at a party or a pool of honey. Those analogies suggest that the Higgs field slows particles down like friction. It doesn't. The Higgs field doesn't slow particles down or create drag. A particle moving through the Higgs field at constant velocity will continue at that same velocity forever. There's no friction. What the Higgs field does is give the particle inertia. It makes the particle resist changes in its velocity. It makes the particle harder to speed up or slow down. Once the particle is moving, it keeps moving at the same speed, unless a force acts on it. But applying that force, changing the particle's motion, requires more effort because the particle now has mass. The Higgs field gives particles the property of inertia, not the property of drag. That's a crucial distinction. Let me try a more precise way of thinking about it. In quantum field theory, which is the mathematical framework that describes all of particle physics, particles are really excitations of quantum fields. An electron isn't a tiny ball. It's a ripple, an excitation in the electron field. A photon isn't a little bullet of light. It's an excitation of the electromagnetic field. Every fundamental particle is an excitation of its corresponding quantum field. These fields fill all of space, and when energy disturbs them in the right way, a particle pops into existence as a vibration in that field. Now, when the Higgs field has its non-zero value everywhere, it interacts with these other quantum fields. Specifically, it couples to them. The strength of this coupling is different for different particles. The electron field couples to the Higgs field with a certain strength. The top quark field couples to the Higgs field with a much greater strength. The photon field doesn't couple to the Higgs field at all. This coupling between a particle's field and the Higgs field is what gives the particle its inertial mass. The stronger the coupling, the larger the mass. It's built into the mathematics of the theory. When you write down the equations describing a particle field interacting with the non-zero Higgs field, a mass term naturally appears in the equations. The particle that was massless before the Higgs field turned on now behaves as though it has mass. It resists acceleration. It moves slower than the speed of light. It can be brought to rest, all because of its interaction with this omnipresent field. Let me make this concrete with some numbers. The electron has a mass of about 0.511 million electron volts. That's very small. The electron couples weakly to the Higgs field. The muon, the electron's heavier cousin, has a mass of about 105.7 million electron volts. It couples more strongly. The top quark, the heaviest fundamental particle we know of, has a mass of about 173 billion electron volts. It couples very strongly to the Higgs field. In fact, the top quark's coupling to the Higgs field is almost exactly 1, which is the strongest coupling in the standard model. The top quark interacts with the Higgs field as intensely as any particle can. The photon, on the other hand, has zero mass. It doesn't couple to the Higgs field at all. The Higgs field is there, filling all of space, and the photon ignores it completely. It passes through as though the field doesn't exist. That's why the photon is massless. That's why it travels at the speed of light. In a very real sense, the speed of light is the default speed of the universe. It's the speed everything would travel at if the Higgs field weren't there. The Higgs field doesn't speed things up. It slows certain things down from the default speed of light by giving them inertial mass. The more a particle interacts with the Higgs field, the more it's slowed from this cosmic speed limit. This is a profound idea. Before the Higgs field settled into its current state, in the earliest moments after the Big Bang, all fundamental particles were massless. All of them traveled at the speed of light. There was no such thing as mass. There was no such thing as rest. Everything moved at the cosmic speed limit. And then, a tiny fraction of a second after the Big Bang, something changed. The Higgs field underwent a phase transition. A phase transition is a sudden change in the state of a system. You experience phase transitions all the time. When water freezes into ice, that's a phase transition. The water molecules rearrange themselves from a disordered liquid into an ordered crystalline solid. The underlying molecules are the same, but the state they're in has changed dramatically. When water boils into steam, that's another phase transition. The liquid becomes a gas. The Higgs field underwent its own kind of phase transition in the very early universe. Before about 10 to the power of negative 12 seconds after the Big Bang, that is, roughly 1 trillionth of a second, the universe was so incredibly hot and energetic that the Higgs field was in a symmetric state. Its value was 0 everywhere. At those extreme temperatures, the field had enough energy to sit at the top of the hill. To use the analogy from before, the symmetry was intact, and because the Higgs field was 0, no particles had mass. Every fundamental particle was massless. The electromagnetic force and the weak nuclear force were unified into a single force called the electroweak force. The W and Z bosons and the photon were all massless and essentially interchangeable. They were different aspects of the same thing. But as the universe expanded and cooled, the temperature dropped below a critical threshold, roughly 10 to the power of 15 degrees, which is about 1 quadrillion degrees. At this point, the Higgs field could no longer sustain its symmetric state. Like a ball perched on top of a hill that finally rolls down, the Higgs field tumbled into its lower energy state, the state with a non-zero value everywhere. This happened everywhere in the universe, essentially simultaneously. The Higgs field went from 0 to its vacuum expectation value of 246 billion electron volts in a cosmic instant. This was one of the most important events in the history of the universe. In fact, it might be the single most consequential moment after the Big Bang itself. When the Higgs field acquired its non-zero value, particles suddenly gained mass. Electrons went from being massless to having their current mass. Quarks acquired mass. The W and Z bosons, which had been massless like the photon, suddenly became heavy. Very heavy. Roughly 80 to 91 times the mass of a proton. The photon, which doesn't interact with the Higgs field, remained massless. It kept traveling at the speed of light, unaffected by the cosmic change that had just reshaped the universe around it. The electroweak force split into 2 separate forces. Electromagnetism, carried by the still massless photon, became a long-range force capable of acting across unlimited distances, the force that holds atoms together and produces light and governs all of chemistry. The weak nuclear force, now carried by the massive W and Z bosons, became a short-range force operating only at subatomic distances, responsible for certain types of radioactive decay. This splitting of the electroweak force into electromagnetism, and the weak force was a direct consequence of the Higgs field settling into its non-zero state. Without the Higgs mechanism, these 2 forces would still be one unified force, and the universe would bear no resemblance to the one we inhabit. This phase transition happened when the universe was roughly 1 trillionth of a second old. Think about that timing. 1 trillionth of a second. Less time than it takes for light to cross a single grain of sand. And in that unimaginably brief instant, the character of the universe changed forever. Particles that had been massless suddenly had mass. Forces that had been unified suddenly split apart. The rules of the game changed in a fraction of a moment. Now, there's an important distinction I need to make very clearly because it confuses a lot of people. The Higgs field and the Higgs boson are not the same thing. The Higgs field is the invisible ocean that fills all of space and gives particles mass. It's always there, it's everywhere. You're immersed in it right now. It's not a particle, it's a field, an entity that has a value at every point in space. The Higgs field, it's what is the work of giving mass to particles. It's the important thing. The Higgs boson, on the other hand, is a particle. Specifically, it's an excitation of the Higgs field. Remember how I said that particles are ripples in quantum fields? An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Well, the Higgs boson is a ripple in the Higgs field. It's what happens when you disturb the Higgs field, when you pump enough energy into a small enough space to create a vibration in this field. Think of it this way. Imagine a calm lake. The lake represents the Higgs field. The water is there even when nothing is happening. It fills the basin. It has a certain depth, a certain level. That level, that ever-present water, is what gives particles mass. It's always there. Now, throw a rock into the lake. The splash and the ripple that spreads outward, that's the Higgs boson. It's a disturbance in the lake, a temporary excitation that eventually dies away. The ripple is not the lake. The lake was there before the ripple and will be there after the ripple fades. But the ripple proves the lake exists. That's exactly what the Higgs boson does. It proves the Higgs field exists. The Higgs boson is the detectable evidence. It's the smoking gun. It's the signature that tells physicists the field is real. You can't directly detect the Higgs field itself. You can't see it or measure it directly any more than you can see the ocean by looking at a single wave. But if you can create a wave, if you can produce a Higgs boson, then you know the ocean is there. The Higgs boson is also unstable. Extremely unstable. It decays almost immediately after being created, in about 1.6 times 10 to the power of negative 22 seconds. That's a decimal, point followed by 21 zeros, and then a 16. That's so fast that the Higgs boson barely has time to exist before it's gone. It never travels more than a tiny fraction of a proton's width before it transforms into other particles. It can decay into pairs of bottom quarks, pairs of W bosons, pairs of Z bosons, pairs of tau leptons, pairs of photons, and other combinations depending on the available energy. These decay products are what physicists actually detect. They never see the Higgs boson directly. They see the debris it leaves behind and work backward to infer that a Higgs boson must have existed briefly before decaying. It's like seeing fireworks in the sky and knowing that a rocket must have launched, even though you never saw the rocket itself. This is a crucial point because it highlights just how different the Higgs field and the Higgs boson are in terms of their roles. The Higgs field is permanent, eternal, filling all of space, doing its job of giving particles mass every moment of every day since the universe was 1/1,000,000th of a second old. The Higgs boson is temporary, fleeting, created in rare high-energy events, and gone almost before it appears. The field is the substance. The boson is just the proof that the substance exists. Now, let me be precise about which particles get their mass from the Higgs field and which do not, because this is where a lot of popular science explanations go wrong. The Higgs field gives inertial mass to certain fundamental particles. These are the elementary particles of the Standard Model that would otherwise be massless. Specifically, the Higgs mechanism gives mass to the W plus boson, the W minus boson, and the Z boson. This is arguably the most important job of the Higgs mechanism, because it's what causes the weak force to be separate from electromagnetism. It's what makes the weak force weak and short-ranged. Without the Higgs field giving mass to these three particles, the electroweak symmetry would be unbroken and the universe would be radically different. The Higgs field also gives mass to all 6 quarks, up, down, charm, strange, top, and bottom. Each quark couples to the Higgs field with a different strength, which is why they have different masses. The up quark has a mass of only about 2.2 million electron volts. The down quark has about 4.7 million electron volts. These are tiny masses. The charm quark has about 1.3 billion electron volts. The strange quark about 96 million electron volts. The bottom quark has about 4.2 billion electron volts. And the top quark, the heavyweight champion of the quark world, has about 173 billion electron volts. These wildly different masses all come from different coupling strengths to the same Higgs field. The Higgs field gives mass to the 3 charged leptons as well. The electron, the muon, and the tau particle all get their inertial mass from interacting with the Higgs field. Again, the different masses reflect different coupling strengths. The electron couples very weakly, giving it a small mass. The tau couples more strongly, giving it a mass about 3,470 times larger than the electrons. Neutrinos are a special and somewhat mysterious case. We know neutrinos have mass because we've observed neutrino oscillations, a phenomenon where neutrinos change from one type to another as they travel through space. This can only happen if neutrinos have mass, but neutrino masses are incredibly tiny, at least 100,000 times smaller than the electron's mass, and possibly much smaller still. Whether neutrinos get their mass from the Higgs field in the same way as other particles or through some different mechanism entirely is still an open question in physics. Some theories propose that neutrinos get their mass through a modified version of the Higgs mechanism. Others propose entirely new mechanisms, involving hypothetical particles called sterile neutrinos that don't interact through any of the known forces. This is one of the most actively studied and unresolved puzzles of modern particle physics. And then there are the massless particles. The photon does not interact with the Higgs field. It passes through the Higgs field as though the field doesn't exist. This is a consequence of the specific way gauge symmetry breaks in the Standard Model. One combination of the original electroweak bosons remains massless, and that combination is the photon. The gluon, the carrier of the strong force, is also massless. Gluons do not interact with the Higgs field either. Both photons and gluons travel at the speed of light, which, as I mentioned, is the default speed, the speed everything would travel at if the Higgs field weren't there. So to summarize what the Higgs field does at the fundamental level, it gives inertial mass to the W and Z bosons, to the 6 quarks, and to the 3 charged leptons. These masses are the inertial masses of elementary particles, meaning they determine how much each particle resists being accelerated. This is the mass that comes directly from a particle's interaction with the Higgs field. It's the original mass, the mass that the Higgs mechanism was invented to explain. But here's something that I really need you to hold on to because it's going to become critical very soon. The masses that the Higgs field gives to quarks are tiny. The up and down quarks, the ones that make up protons and neutrons, have masses of only a few million electron volts each. If the proton's mass were simply the sum of the masses of the quarks inside it, it should weigh only about 9 or 10 million electron volts. But the actual measured mass of a proton is about 938 million electron volts. That's roughly 100 times heavier than the combined masses of its quarks. The quarks make up less than 1% of the proton's total mass. Less than 1%. The Higgs field, for all its importance, for all its elegance, for all the billions of dollars spent confirming its existence, accounts for less than 1% of the mass of a proton. And since protons and neutrons make up essentially all the visible mass in the universe, since every atom in your body, every star in the sky, every planet and moon and asteroid is built primarily from protons and neutrons, this means the Higgs field is responsible for less than 1% of the mass of the everyday world. Less than 1% of the mass of your body. Less than 1% of the mass of the Earth. Less than 1% of the mass of the Sun. If you weigh, say, 70 kilograms, then only about 700 grams of that, less than 2 pounds, comes from the Higgs field giving mass to the quarks and electrons in your body. The other 69.3 kilograms comes from somewhere else entirely. Somewhere that has nothing to do with the Higgs field. Somewhere that most people have never even heard of. So where does the rest of your mass come from? What accounts for the other 99%? What is it about a proton that makes it so vastly heavier than the quarks inside it? This is one of the most astonishing facts in all of physics, and the answer connects to something Einstein told us more than a century ago. Something so fundamental that it's written on t-shirts and coffee mugs around the world, even though almost nobody truly understands what it means. The answer to where 99% of your mass comes from will take us to the heart of the strong nuclear force, to the chaotic interior of the proton, and to the deepest connection between energy and matter that physics has ever uncovered. And it will reveal that mass, the most tangible property of the physical world, the thing that makes matter feel solid and substantial, is mostly not what you think it is at all. So physicists had this extraordinary theory, a field that fills all of space, a field that gives mass to fundamental particles, a field that explains why the weak force is different from electromagnetism, a field that explains why the universe has structure, why atoms exist, why you exist. It was elegant. It was mathematically consistent. It solved one of the deepest problems in physics, but it was still just a theory, a set of equations written on paper. And in science, equations on paper mean nothing unless they can be tested against reality. The universe doesn't owe us elegance, it does what it does. The only way to know if the Higgs field was real was to find direct evidence for it. And the most direct evidence would be the Higgs boson, that ripple in the Higgs field that the theory predicted should exist. But finding the Higgs boson was going to be extraordinarily difficult. The theory predicted that the particle existed, but it didn't predict its exact mass. The Higgs boson could have had a mass anywhere in a wide range, from a few billion electron volts to about 1,000 billion electron volts. That's a huge window, and the mass of the particle determines how much energy you need to create it. Because in particle physics, creating a particle means converting energy into mass according to Einstein's famous equation. The higher the mass, the more energy you need. This meant physicists needed particle accelerators, machines that accelerate particles to nearly the speed of light, and then smash them together. The energy released in those collisions can briefly create new particles that don't normally exist in nature. The higher the collision energy, the heavier the particles you can create. It's like needing a bigger hammer to break a harder rock. If the Higgs boson was light, you might find it with a relatively modest accelerator. If it was heavy, you'd need something much more powerful. The search began almost immediately after the theory was proposed in the 1960s, though the earliest accelerators didn't have nearly enough energy. The first serious attempt came in the 1980s and 90s at CERN, the European Organization for Nuclear Research, located on the border between Switzerland and France near Geneva. CERN operated a particle accelerator called the Large Electron Positron Collider, or LEP, which ran from 1989 to 2000. LEP was a circular tunnel about 27 kilometers in circumference, roughly 17 miles, buried underground beneath the French and Swiss countryside. Inside this tunnel, electrons and their antimatter counterparts, positrons, were accelerated in opposite directions and then smashed together at high speeds. LEP didn't find the Higgs boson. It wasn't powerful enough, but it did something almost as important. It narrowed down where the Higgs boson could be hiding. By not finding the particle up to a certain energy level, LEP was able to establish that the Higgs boson, if it existed, must have a mass greater than about 114.4 billion electron volts. This might sound like a failure, but it wasn't. Not at all. Ruling out possibilities is a crucial part of scientific progress. Every energy range that was searched and came up empty told physicists where the Higgs boson wasn't. And knowing where it isn't helps you figure out where it might be. Across the Atlantic, the United States was building its own machine to search for the Higgs boson. It was called the Superconducting Super Collider, or SSC, and it was going to be the most powerful particle accelerator ever built. The tunnel would have been 87 kilometers in circumference, more than 3 times longer than LEP's tunnel. It was being constructed in Waxahachie, Texas, and it would have reached collision energies of 40 trillion electron volts, far beyond anything else in existence or even planned at the time. The SSC would almost certainly have found the Higgs boson. It was designed with enough energy and sensitivity to discover the particle across its entire predicted mass range. If it had been completed, the Higgs boson might have been discovered in the late 1990s, more than a decade before it actually was. But in 1993, the United States Congress cancelled the project. The reasons were primarily financial. The estimated cost had ballooned from about $4.4 billion to over $11 billion. The Cold War had ended, reducing the political motivation for big science projects. There was skepticism among politicians about spending billions of dollars on fundamental research with no obvious practical application. The tunneling was already about a quarter complete when the project was killed. Billions of dollars had been spent. Thousands of scientists and engineers lost their jobs, and the most powerful particle accelerator ever conceived was abandoned. Its partially dug tunnels eventually filled in with dirt. The cancellation of the Superconducting Super Collider was a devastating blow to American particle physics. It shifted the center of gravity of high-energy physics research from the United States to Europe, specifically to CERN, and it meant that the search for the Higgs boson would fall to a new machine that CERN was planning to build in the same tunnel that had housed LEP. That machine would become the most complex, most expensive, and most ambitious scientific instrument ever constructed by human beings. It was called the Large Hadron Collider, or LHC. The Large Hadron Collider is difficult to describe without resorting to superlatives, because everything about it is extreme. The tunnel is 27 kilometers in circumference, a massive ring buried about 100 meters underground, straddling the Swiss-French border. Inside this tunnel are 2 parallel beam pipes, each containing a beam of protons traveling in opposite directions at very nearly the speed of light. The protons are accelerated by powerful electric fields and kept on their circular path by 1,232 superconducting dipole magnets. each about 15 meters long and weighing approximately 35 tons. These magnets generate fields of about 8.3 Tesla, which is roughly 170,000 times stronger than Earth's magnetic field. To achieve superconductivity, the magnets must be cooled to a temperature of 1.9 kelvins, which is negative 271.3 degrees Celsius. That's colder than the cosmic microwave background radiation that fills outer space, which is about 2.7 kelvins. The LHC is one of the coldest places in the known universe. The protons inside the LHC travel at 99.999991% of the speed of light. At this speed, a proton completes the 27-kilometer loop about 11,245 times per second. Each beam contains roughly 300 trillion protons, organized into bunches. The two beams cross at 4 specific points around the ring, and at those crossing points, protons from opposite beams collide head-on. There are about 600 million proton-proton collisions per second when the machine is operating at full capacity. Each collision produces a spray of particles that fly outward from the collision point at nearly the speed of light. At each of these 4 collision points, massive particle detectors surround the beam crossing to capture the debris from the collisions. The 2 largest detectors are called Atlas and CMS. These are the instruments that would ultimately discover the Higgs boson. Atlas is about 46 meters long, 25 meters in diameter, and weighs about 7,000 tons. CMS is slightly more compact but considerably heavier, about 21 meters long, 15 meters in diameter, and weighing about 14,000 tons. Both detectors are layered instruments built like enormous technological onions. Each layer is designed to detect and measure different types of particles produced in the collisions. Together, they capture the positions, energies, and trajectories of the particles spraying outward from every collision. The amount of data generated by the LHC is staggering. Each of those 600 million collisions per second produces raw data. If you tried to record everything, you'd generate about 1 petabyte of data per second. That's 1 million gigabytes every single second. No storage system on Earth could handle that. So the detectors use sophisticated trigger systems, essentially fast algorithms that examine each collision in real time and decide within microseconds whether it looks interesting enough to keep. Only about 1 in every million collisions is actually recorded. And even then, the LHC generates about 1 petabyte of stored data per day when running. This data is processed by a worldwide network of computing centers called the Worldwide LHC Computing Grid, connecting more than 170 computing facilities in 42 countries. The grid processes about 2 million computing jobs per day. Building the LHC took about 10 years and cost approximately $9 billion. More than 10,000 scientists, engineers, and technicians from over 100 countries contributed to its construction. The first beams circulated on September 10th, 2008, which was a historic moment. But just 9 days later, disaster struck. A faulty electrical connection between 2 magnets caused an electrical arc that punctured the liquid helium cooling system. 6 tons of liquid helium leaked into the tunnel, causing an explosion that damaged over 50 magnets along a 750-meter stretch of the tunnel. The accident set the project back over a year and cost about $40 million to repair. It was a devastating setback, but the machine was eventually repaired and restarted. When the LHC began full physics operations in 2010, the race to find the Higgs boson entered its final stretch. Both the ATLAS and CMS experiments began collecting data from proton-proton collisions at unprecedented energies. They were looking for the Higgs boson, but finding it meant looking for an incredibly rare signal buried in an enormous amount of noise. Here's the challenge. The Higgs boson is produced in only about 1 out of every 10 billion proton-proton collisions at the LHC. That's an almost impossibly rare event. And when a Higgs boson is produced, it decays almost instantly into other particles. Those other particles look very similar to the debris from ordinary collisions that don't involve a Higgs boson at all. Imagine trying to find a specific grain of sand on a beach where every grain looks almost identical. You'd need to examine billions of grains, looking for incredibly subtle differences that distinguish the special grain from all the ordinary ones. The physicists used a clever approach. They couldn't detect the Higgs boson directly because it decays too quickly. Instead, they looked for the particles it decayed into and tried to find statistical patterns that would indicate a Higgs boson had been briefly present. One of the cleanest decay channels was the Higgs boson decaying into 2 photons. The theory predicted that if you measured the combined energy of pairs of photons from millions of collisions and plotted the results on a graph, you'd see a small bump at the energy corresponding to the Higgs boson's mass. The bump would be subtle, rising just slightly above the smooth background of ordinary photon pairs. But if enough data was collected, the bump would become statistically significant, unmistakable evidence that something was creating those photon pairs, and that something would be the Higgs boson. Throughout 2011 and into 2012, both ATLAS and CMS collected more and more data. The statistical significance of the bump slowly grew. At first it was barely visible, a faint suggestion that something might be there. Then it grew stronger. By late 2011, both experiments were seeing hints. Tantalizing hints. Not strong enough to claim a discovery, but strong enough that physicists started getting excited. The bump was appearing at a mass of about 125 billion electron volts. Both experiments, using completely independent detectors and analysis methods, were seeing a signal at the same mass. That consistency was extremely encouraging. In particle physics, you need a statistical significance of 5 sigma before you can claim a discovery. Sigma is a measure of how unlikely it is that the signal you're seeing is just a random statistical fluctuation, a fluke. 1 sigma means there's about a 1 in 3 chance it's a fluke. Not convincing at all. 2 sigma is about a 1 in 20 chance. Still not convincing. 3 sigma is about a 1 in 740 chance. Interesting, but not enough. Physicists have been fooled by 3 sigma signals before. They've disappeared with more data. 5 sigma is about a 1 in 3.5 million chance that the signal is a fluke. That's the gold standard for particle physics discoveries. It's an extremely high bar, deliberately so. If the probability that your signal is random noise is less than 1 in 3.5 million, you can claim you found something real. By late June 2012, both experiments were approaching the 5 sigma threshold. CERN scheduled a special seminar for July 4th, 2012. The rumors were flying. Physicists around the world suspected what was coming. The day of the announcement arrived and the auditorium at CERN was packed. Peter Higgs, then 83 years old, was in the audience. So was François Englert, then 79. These were two of the men who had proposed the theory nearly half a century earlier. They had waited almost 50 years to find out if they were right. Fabiola Gianotti, the spokesperson for the Atlas experiment, presented first. She showed the data, the graphs, the bump at 125 to 126 billion electron volts. The statistical significance for Atlas was 5.9 sigma. Then Joe Incandela, the spokesperson for CMS, presented. His experiment, using completely different technology and independent analysis, showed a bump at the same mass. The CMS significance was 5 sigma exactly. 2 independent experiments using different detectors and different methods had both found a new particle at the same mass, each with a statistical significance exceeding the discovery threshold. Rolf Dieter Hoyer, the Director General of CERN at the time, stood up after both presentations and said, "I think we have it." The room erupted. Scientists who had worked on this problem for decades, some for their entire careers, were openly emotional. Peter Higgs was seen wiping tears from his eyes. He later said, "It's really an incredible thing that it's happened in my lifetime." François Englert looked overwhelmed, shaking his head slowly as though he couldn't quite believe what he was hearing. The discovery was announced to the world on July 4th, 2012. It made headlines everywhere: newspapers, television, websites, social media. People who had never heard of particle physics suddenly knew the phrase Higgs boson. The discovery was hailed as one of the greatest scientific achievements of the century. And it was. This wasn't just finding a new particle. This was confirming the existence of a completely new type of field. A field that permeates all of space and gives mass to fundamental particles. It was validating a theory that had been proposed nearly 50 years earlier, and that underpinned our entire understanding of why the universe has structure. In October 2013, Peter Higgs and François Englert were awarded the Nobel Prize in Physics for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles. The Nobel Committee specifically cited the confirmation by the Atlas and CMS experiments at CERN. It was one of the longest waits in Nobel Prize history, nearly 50 years between the theoretical prediction and the experimental confirmation. Robert Brute, who had co-authored the paper with Englert, had died in 2011, just 1 year before the discovery. He did not live to see the confirmation of his work, and the Nobel Prize is not awarded posthumously. Gerald Guralnick, Carl Hagen, and Tom Kibble, the third group who independently proposed the mechanism, did not receive the Nobel Prize. The prize is limited to a maximum of 3 recipients, and the committee chose to honor Higgs and Englert. This decision was controversial in some quarters of the physics community, as all 3 groups contributed to the theory. But such is the nature of the Nobel Prize. It cannot always fully acknowledge the collaborative and independent nature of scientific discovery. Now, what exactly did the discovery prove? What do we now know that we didn't know before? The discovery confirmed several things. First, the Higgs field exists. This is the most fundamental conclusion. The Higgs boson is an excitation of the Higgs field, and its detection proves the field is real. The invisible ocean that fills all of space, the thing that gives mass to fundamental particles, it's actually there. Second, The mass of the Higgs boson was measured at about 125.1 billion electron volts, with a small uncertainty. This was within the range predicted by the Standard Model, though the theory didn't predict a specific value. The measured mass has important implications. It tells us about the stability of the Higgs field and whether the universe is in a stable state or merely a metastable one. We'll touch on that shortly. Third, the discovery confirmed the mechanism of electroweak symmetry breaking. The W and Z bosons get their masses from the Higgs mechanism, exactly as the theory predicted. Fourth, the properties of the discovered particle were consistent with the Standard Model predictions. Its spin was measured as 0, making it the first fundamental scalar particle ever discovered. All other known fundamental particles have spin of 1/2 or 1. The Higgs boson is unique in this regard, but the discovery also left many questions unanswered. The Standard Model doesn't predict the mass of the Higgs boson. It emerged at 125 billion electron volts. But the theory doesn't explain why it has that particular mass rather than some other value. The masses of the fundamental particles that interact with the Higgs field, the quarks and leptons, are also not predicted by the theory. The Standard Model tells us that these particles get their mass from coupling to the Higgs field, but it doesn't tell us why the coupling strengths have the specific values they do. Why is the electron so light? Why is the top quark so heavy? Why is the muon about 207 times heavier than the electron when they're otherwise identical particles? These coupling strengths are free parameters of the Standard Model. They're numbers that must be measured experimentally and then inserted into the theory by hand. The theory works with whatever values you put in, but it doesn't explain those values. It's as if the theory gives you a recipe but doesn't explain why the recipe calls for those specific amounts of each ingredient. There's also the hierarchy problem. The measured mass of the Higgs boson is about 125 billion electron volts. But when physicists calculate what the mass should be, including the effects of quantum corrections from virtual particles constantly popping in and out of existence, they find that the natural mass should be enormously higher, perhaps as high as 10 to the power of 19 billion electron volts. That's the Planck scale, the energy scale where gravity becomes as strong as the other forces. The fact that the Higgs boson's mass is so much lower than this natural scale requires an extraordinary fine-tuning of the theory's parameters. Values must cancel out to astonishing precision, about 1 part in 10 to the power of 34, to produce the observed mass. This doesn't mean the theory is wrong. The cancellation clearly happens because we've measured the mass, but physicists find it deeply unsatisfying. It feels like there should be some deeper explanation, some mechanism that naturally produces a light Higgs boson without requiring such extraordinary coincidences. Many physicists expected that the LHC would discover not just the Higgs boson, but also new physics, beyond the Standard Model that would explain the hierarchy problem. Supersymmetry, a theoretical framework that predicts a partner particle for every known particle, was a leading candidate. Supersymmetry would naturally explain why the Higgs boson is so light, but as of the mid-2020s, the LHC has found no evidence for supersymmetry or any other new physics beyond the Standard Model. The Higgs boson sits at 125 billion electron volts, seemingly fine-tuned, and we don't know why. The measured mass of the Higgs boson also raises questions about the ultimate fate of the universe. Calculations suggest that at 125 billion electron volts, the Higgs field might not be in its lowest possible energy state. It might be in what physicists call a metastable state, like a ball sitting in a shallow valley partway up a mountain rather than at the very bottom. The ball seems stable, it's not moving, it's sitting comfortably in its litty valley, but there's a lower valley further down the mountain. If the ball were somehow given enough energy to get over the ridge between the two valleys, it would roll down to the true minimum and never come back. If the Higgs field is metastable, then in principle, it could tunnel to a lower energy state through a quantum mechanical process. If this happened, a bubble of true vacuum would form and expand at nearly the speed of light, converting the Higgs field to its new lower value everywhere it touched. Inside this bubble, the Higgs field would have a different value. The masses of all fundamental particles would change. The properties of atoms would change. Chemistry would stop working the way it does. Any structure built from atoms, including you, will be instantly destroyed. The bubble would be undetectable before it arrived, because it expands at nearly the speed of light. There would be no warning. One moment, everything is normal. The next moment, the laws of physics in your region of space have changed, and everything you know has ceased to exist. Now, before you lose sleep over this, let me be very clear. Even if the Higgs field is metastable, the probability of such a transition happening is extraordinarily small. The expected lifetime of the metastable state is calculated to be vastly longer than the current age of the universe, perhaps 10 to the power of 100 years or more. The universe is only about 13.8 billion years old, so the probability of vacuum decay happening anytime soon is essentially zero. You are far more likely to be struck by lightning while being eaten by a shark during an earthquake than you are to be destroyed by vacuum decay in your lifetime. The calculation is interesting from a theoretical standpoint, but it's not something you need to worry about practically. Since the discovery in 2012, physicists at the LHC have been studying the Higgs boson in greater and greater detail. They've measured how it decays, how often it's produced, how it interacts with other particles. And so far, every measurement is consistent with the Standard Model's predictions. The Higgs boson behaves exactly as the theory says it should. This is simultaneously reassuring and frustrating. Reassuring because it confirms the theory works. Frustrating because physicists were hoping to find deviations from the Standard Model, hints of new physics, clues about what lies beyond our current understanding. So far, the Standard Model has passed every test flawlessly. The LHC has undergone upgrades since the original discovery. It now operates at higher energies and produces more collisions per second. A major upgrade called the High Luminosity LHC is planned to begin operations around 2029. This upgrade will increase the number of collisions by a factor of 5 to 10, allowing much more precise measurements of the Higgs boson's properties. Physicists hope that with more data, they might detect tiny deviations from the Standard Model predictions. Even a small discrepancy could point the way to new physics, to a deeper theory that explains the things the Standard Model can't. The discovery of the Higgs boson was a triumph of human ingenuity, collaboration, and persistence. Nearly 50 years passed between the theoretical prediction and the experimental confirmation. Billions of dollars were spent. Tens of thousands of people contributed. The most complex machine in human history was built. And in the end, nature confirmed what a handful of theorists had proposed in 1964. There is a field that fills all of space. That field gives mass to fundamental particles, and when you disturb that field with enough energy, a particle appears briefly before vanishing back into the invisible ocean from which it came. But as I hinted earlier, there's a twist to this story that many people don't know, a twist that changes everything about how you should think about mass. Because the Higgs field, for all its importance, for all the decades of searching and the billions spent finding its signature, is only part of the answer to the question of where mass comes from. In fact, it's the smaller part, much smaller. The Higgs field accounts for a tiny fraction of the mass of the everyday world. And the rest? The overwhelming majority of the mass of everything you see and touch and experience comes from something else entirely. Something older in our understanding, something hiding in plain sight inside every atom in your body, something that connects directly to the most famous equation in the history of science. And understanding it will change how you see not just mass, but the very nature of what matter is. So here we are. We've learned what the Higgs field is. We've understood how it gives mass to fundamental particles. We've followed the incredible story of how physicists built the most complex machine in history to confirm its existence. And you might think that's the end of the story. The Higgs field gives particles mass. Mystery solved. Case closed. But it's not, because the Higgs field, remarkable as it is, answers only a small part of the question. And the part it doesn't answer is, frankly, the bigger and more astonishing part. Let me show you why. You are made of atoms. Every cell in your body, every drop of blood, every strand of hair, every thought firing through your brain, all of it is built from atoms. And every atom has a nucleus at its center made of protons and neutrons. The overwhelming majority of your mass, the mass you feel when you step on a scale, the mass that keeps you anchored to the ground, comes from those protons and neutrons. Electrons contribute almost nothing. An electron is about 1,836 times lighter than a proton. So even though your body contains roughly the same number of electrons as protons, the electrons account for less than 1/20th of 1% of your total mass. Your mass is essentially the mass of your protons and neutrons. Everything else is rounding error. Now, a proton is made of 3 quarks, 2 up quarks and 1 down quark, bound together by the strong nuclear force. We know the masses of these quarks because the Higgs field gives them their inertial mass, and we've measured those masses through decades of experiments. An up quark has a mass of about 2.2 million electron volts. A down quark has a mass of about 4.7 million electron volts. So if you add up the masses of the 3 quarks inside a proton, 2 up quarks at 2.2 each plus 1 down quark at 4.7, you get about 9.1 million electron volts. But the measured mass of a proton is 938.3 million electron volts. The quarks contribute about 9.1 million electron volts. The proton weighs 938.3 million electron volts. The quarks account for less than 1% of the proton's mass. Less than 1%. The Higgs field, which gives those quarks their mass, is responsible for less than 1% of what a proton actually weighs. So, where does the other 99% come from? What makes a proton so much heavier than the sum of its parts? The answer is energy. Specifically the energy of the strong nuclear force raging inside the proton. And to understand this, we need to talk about Einstein's most famous equation. An equation so well known that it appears on bumper stickers and t-shirts and coffee mugs. An equation that almost everyone has seen, but very few people truly understand. E equals mc squared. Albert Einstein published his theory of special relativity in 1905. Among the many revolutionary conclusions of that theory was the equivalence of mass and energy. Energy and mass are not separate things. They are the same thing expressed in different units. Mass is a form of energy. Energy is a form of mass. You can convert one into the other. The equation tells you exactly how. EA equals mc squared. Energy equals mass multiplied by the speed of light squared. The speed of light squared is an enormous number, about 9 times 10 to the power of 16 meters squared per second squared. This means that a tiny amount of mass contains a staggering amount of energy. And conversely, a large amount of energy can manifest as what we experience as mass. This equation isn't just a theoretical curiosity. It's been confirmed countless times. Nuclear power plants convert a tiny fraction of the mass of uranium atoms into enormous amounts of energy through nuclear fission. The sun converts about 4 million tons of mass into energy every single second through nuclear fusion, and that energy is what lights up our solar system and makes life on Earth possible. When a particle and its antiparticle meet and annihilate each other, their mass is converted entirely into energy in the form of photons. When physicists create new particles and accelerators, they're converting the kinetic energy of the colliding particles into the mass of new particles. Mass and energy are interchangeable. They're different faces of the same coin. Now, here's where this connects to the proton. Inside a proton, there's an extraordinary amount of energy. The 3 quarks aren't just sitting there quietly. They're trapped in an incredibly small space, roughly 1 femtometer across, which is 1 quadrillionth of a meter, and they're bound together by the strong nuclear force, which is carried by particles called gluons. But the strong force doesn't behave like any force you've experienced in everyday life. It's profoundly strange, and its strangeness is the key to understanding where most of your mass comes from. The strong force is described by a theory called quantum chromodynamics, or QCD. It's one of the most mathematically challenging and counterintuitive theories in all of physics. In quantum chromodynamics, quarks carry a property called color charge. This has absolutely nothing to do with actual colors. It's just a label physicists use because, like actual colors, there are 3 types: red, green, and blue. Every quark carries one of these 3 color charges. Antiquarks carry anti-red, anti-green, or anti-blue. Gluons, the particles that carry the strong force, themselves carry color charge as well. This is unlike anything in electromagnetism. Photons carry the electromagnetic force, but photons are electrically neutral. They don't carry the charge they transmit. Gluons do. They carry the very color charge that they're transmitting between quarks. This seemingly technical difference has profound consequences. Because gluons carry color charge, they don't just transmit force between quarks, they also interact with each other. Gluons pull on other gluons. They can emit more gluons. They form a tangled, seething web of interactions inside the proton. Imagine a room where every person is shouting, and everyone who hears shouting starts shouting louder, and everyone who hears that starts shouting even louder still. That's something like what happens inside a proton. The gluon field is in a constant state of violent agitation, a roiling storm of energy that never stops and never calms down. This leads to one of the most remarkable properties of the strong force, a property called confinement. You cannot isolate a single quark, ever. If you try to pull a quark out of a proton, the strong force between the quark and the other quarks doesn't decrease with distance the way gravity or electromagnetism does. Instead, it stays constant or even increases. The energy stored in the gluon field between the quarks keeps growing as you try to separate them. It's like stretching a rubber band. The farther you pull, the more energy is stored in the band. But here's what happens. If you pull hard enough, if you put enough energy into trying to separate the quarks, the energy stored in the gluon field becomes so great that it spontaneously creates a new quark-antiquark pair out of pure energy. Instead of freeing a single quark, you've created new quarks. The original quark pairs up with the newly created antiquark to form a new particle called a meson. The other quarks rearrange themselves into another bound state. You end up with more particles, but no free quarks. You can never win. The quarks are permanently confined inside composite particles. This confinement has been tested experimentally in particle accelerators. When protons are smashed together at high energies, you don't see individual quarks flying out. You see jets, sprays of composite particles, mesons and baryons that form almost instantly as the quarks and gluons from the collision rearrange themselves into new bound states. The energy of the collision creates new quark-antiquark pairs, which immediately bind together. Free quarks have never been observed. Not once. Not in any experiment ever performed. As far as we know, they cannot exist in isolation under any circumstances in the current state of the universe. Now, let's come back to the mass of the proton. Inside the proton, the three quarks are moving at enormous speeds, close to the speed of light, confined to that tiny space of about 1 femtometer. They're bouncing around, ricocheting off the gluon field, constantly exchanging gluons with each other. The gluon field itself is a churning sea of energy. Gluons are constantly being emitted and absorbed. They're splitting into pairs of gluons. They're creating a virtual quark-antiquark pairs that pop into existence and then annihilate each other in unimaginably short time spans. The inside of a proton is not a calm, orderly place with three quarks neatly arranged. It's a storm, a violent, chaotic, seething storm of quantum fields and virtual particles and energy. All of this activity, the kinetic energy of the quarks, moving at nearly the speed of light, the energy of the gluon field constantly churning, the energy of virtual quark-antiquark pairs popping in and out of existence, all of it contributes to the proton's mass, because energy is mass. Einstein told us that. E equals mc squared. The enormous energy inside the proton, the energy of the strong force in all its chaotic glory, manifests as mass. This is where 99% of the proton's mass comes from. Not from the Higgs field giving quarks their intrinsic mass, not from anything solid or material in the conventional sense. From energy. From the energy of quantum fields interacting inside a space smaller than a trillionth of a millimeter. Let me be more specific about the breakdown. Physicists have calculated, using incredibly complex computer simulations of quantum chromodynamics performed on supercomputers, exactly how the proton's mass is distributed. These calculations, called lattice QCD calculations, divide space into a grid and compute the behavior of the strong force at each point on the grid. They're some of the most computationally demanding calculations in all of science. And the results are remarkable. Roughly half of the proton's mass comes from the kinetic energy of the quarks and gluons moving inside it. The quarks are moving at speeds close to the speed of light, and their kinetic energy, through Einstein's equation, contributes mass. The gluons, which are themselves massless particles, also carry enormous kinetic energy as they zip around inside the proton. That kinetic energy manifests as mass. Another roughly 1/3 comes from the energy of the gluon field itself, the energy stored in the strong force field that permeates the interior of the proton. And the remaining fraction comes from quantum effects, the energy of virtual particle-antiparticle pairs and other quantum fluctuations. A landmark result came in 2008 when a team led by physicist Stefan Dürr published a paper in the journal Science showing that lattice QCD calculations could reproduce the masses of protons, neutrons, and other hadrons from first principles. Starting with just the quark masses from the Higgs interaction and the strength of the strong force, the calculations produce the correct proton mass to within a few % accuracy. This was extraordinary. It showed that we genuinely understand where the proton's mass comes from. It's not a mystery. It's not unexplained. The energy of the strong force inside the proton, computed from the fundamental equations of quantum chromodynamics, gives you the right answer. The mass of the proton is almost entirely binding energy from the strong force, with only a tiny contribution from the Higgs-generated quark masses. Think about what this means for you personally. Your body contains roughly 7 billion atoms. That's 7 times 10 to the power of 27. Each atom has a nucleus made of protons and neutrons. And in every single one of those protons and neutrons, 99% of the mass comes from the energy of the strong force, not from the Higgs field. When you step on a scale and see a number, 99% of that number is the energy of gluon fields and quark motion inside your atomic nuclei. You are, in the most literal sense, made of energy. Not in some vague metaphysical way, not as a figure of speech. In a precise, quantitative, experimentally verified, scientifically rigorous way. You are made of energy that manifests as mass because of Einstein's equation. This is perhaps the most profound thing physics has ever told us about the nature of matter. The stuff of the world. The material that makes up everything you see and touch and feel isn't really stuff at all. Not in the way you might imagine. When you knock on a table and feel its solidity, when you pick up a rock and feel its weight, when you feel the ground beneath your feet, what you're experiencing is almost entirely the energy of quantum fields trapped inside protons and neutrons. The solidity, the heaviness, the substance of the physical world is energy, confined, concentrated, packaged into tiny nuclear scale volumes, but energy nonetheless. This means that mass isn't a single simple thing. It arises from at least two fundamentally different sources. The first source is the Higgs field. This is what gives inertial mass to elementary particles, the fundamental quarks and leptons, and W and Z bosons. It's the mass that comes from a particle's interaction with the Higgs field that permeates all of space. This type of mass is intrinsic to the elementary particle. It's the mass the particle has by itself, independent of what it's bound to or how fast it's moving. For quarks, these masses are small. For the electron, it's tiny. For the W and Z bosons, it's substantial. But for the building blocks of everyday matter, the up quark, the down quark, and the electron, the Higgs-generated masses, are tiny compared to the masses of the composite structures they form. The second source is binding energy. This is the mass that arises from the energy of the strong force inside protons and neutrons. It's not intrinsic to any individual particle. It's a property of the system, of the bound state, of the interactions between particles. It comes from kinetic energy, from field energy, from quantum fluctuations. It's mass that exists, because energy is mass. This is the dominant source of mass in the everyday world. It's 99% of the mass of a proton, 99% of the mass of a neutron, and therefore 99% of the mass of every atom, every molecule, every object, every person, every planet, every star. Understanding this distinction changes how you should think about the physical world. When you lift a heavy object, most of the resistance you feel isn't coming from the Higgs field. It's coming from the energy of gluon fields inside the nuclei of the atoms in that object. When Earth's gravity pulls on you, it's pulling on the energy trapped inside your protons and neutrons. When astronomers measure the mass of a star, they're mostly measuring the energy of the strong force inside the trillions upon trillions of protons and neutrons that make up that star. The Higgs field is essential, as we've seen, for setting the conditions that allow matter to exist at all. It gives fundamental particles just enough mass for them to bind together and form structures. But the overwhelming majority of the mass that results from those structures comes from the strong force, not from the Higgs field. There's something almost poetic about this. The universe is not made of things. It's made of interactions. It's made of fields talking to other fields, energy transforming from one form to another, forces binding particles together so tightly that the binding energy itself becomes the dominant form of mass. The solid, tangible, weighty world around you is, at its deepest level, a dance of energy. The atoms in your hand aren't little solid balls. They're mostly empty space filled with quantum fields. The nucleus at the center of each atom is 100,000 times smaller than the atom itself. And even the nucleus is a seething cloud of quarks and gluons rather than a solid lump. The mass you feel when you press your hand against a table is the energy of those fields resisting compression. You never actually touch anything. The electrons in your hand repel the electrons in the table through the electromagnetic force, and what you feel as contact is really the force of electromagnetic fields pushing against each other. And the mass of your hand and the mass of the table, the mass that gives both objects their physical presence, is overwhelmingly the energy of the strong force trapped inside their atomic nuclei. Let me take this one step further. If the Higgs field was somehow switched off, if you could magically remove it from the universe, quarks would become massless, electrons would become massless, the W and Z bosons would become massless, and the weak force would unify with electromagnetism. This would be catastrophic for atomic structure. Massless electrons couldn't be bound to nuclei because the electromagnetic force would change character without the separation from the weak force. Atoms as we know them couldn't exist. Chemistry would cease. Life would be impossible. But here's what's remarkable. The proton wouldn't disappear. The proton would still have most of its mass. Lattice QCD calculations show that even if you set the quark masses to 0, if you completely remove the Higgs contribution, the proton would still have a mass of roughly 880 million electron volts. That's only about 6% less than its actual mass of 938 million electron volts. The strong force would still confine the quarks. The gluon field would still churn with energy, and that energy would still manifest as mass. The proton's mass is overwhelmingly independent of the Higgs field. It comes from the dynamics of the strong force, and the strong force doesn't need the Higgs field to do its job. This tells us something deep about the nature of mass. Mass is not one phenomenon, it's at least two phenomena masquerading as the same thing. The inertial mass of an electron from the Higgs field and the mass of a proton from binding energy are fundamentally different in origin, yet they behave identically. They both resist acceleration. They both respond to gravity. They both contribute to the curvature of space-time in general relativity. There is no experiment that can distinguish Higgs-generated mass from binding energy mass. They are equivalent in every measurable way. This equivalence isn't something we've derived from first principles, it's an observed fact, and nobody fully understands why it should be true. Why should mass from the Higgs field and mass from the energy of gluon fields respond to gravity in exactly the same way? Einstein's equivalence principle says they must, and every experiment confirms it. But the deeper reason why remains one of the open questions of physics. So where does this leave us? What should you take away from everything we've explored tonight? First, mass is not what you thought it was. It's not some intrinsic substance baked into particles from the beginning of time. It's acquired. It's emergent. It comes from interactions, from fields, from energy. The Higgs field gives fundamental particles their inertial mass, but that's only the start of the story. The vast majority of mass in the universe comes from the binding energy of the strong force, from the violent quantum storm raging inside every proton and neutron, in every atom. Second, you are made of energy. This isn't mysticism. This isn't metaphor. This is quantitative physics confirmed by experiment. 99% of your mass is the energy of quantum chromodynamic fields inside your atomic nuclei. When you feel heavy, what you're feeling is the energy of the strong force manifested as mass through Einstein's E equals mc squared. The solidity of the world is energy. The weight of your body is energy. The substance of everything you've ever held in your hands is overwhelmingly energy, not stuff. Third, the universe is stranger and more beautiful than it appears. The table in front of you looks solid and permanent, but it's mostly empty space filled with quantum fields. Its mass comes primarily not from any material substance, but from the energy of forces binding its constituent particles together. The ground beneath your feet feels firm and immovable, but its firmness and its mass are the products of quantum field interactions happening at scales billions of times smaller than you can see. Reality at its deepest level is nothing like our everyday experience suggests. It's wilder, more dynamic, more interconnected, and more beautiful than our senses could ever reveal. And finally, the story isn't over. Physicists still don't understand why the Higgs field has the particular strength it does. They don't know why different particles couple to it with different strengths. They don't know how to reconcile the Higgs mechanism with gravity. They don't know if the Higgs boson is truly fundamental, or if it's a composite particle made of something deeper. They don't know if there are additional Higgs fields beyond the one we've discovered. They don't know why the proton's mass takes the exact value it does, though they can calculate it. They don't know why mass from the Higgs field and mass from binding energy are equivalent. Each answer has opened new questions. Each discovery has revealed new mysteries. The origin of mass is understood far better today than it was 60 years ago, but it's not fully understood. Not yet. Perhaps not for a long time. But that's what makes physics beautiful. The questions keep coming. The universe keeps surprising us. Every time we think we've reached the end of the story, we find another chapter waiting. So tonight, we've explored one of the deepest questions in all of science. Why does mass exist? The answer involves two remarkable mechanisms. The Higgs field, an invisible quantum field that fills every point in the universe and gives fundamental particles like quarks and electrons their intrinsic inertial mass through direct interaction. And the binding energy of the strong nuclear force, the violent energy of gluon fields and quark motion inside protons and neutrons, that accounts for the overwhelming majority of mass in the everyday world through Einstein's equivalence of energy and mass. Both are essential. The Higgs field creates the conditions for matter by giving fundamental particles their inertial mass. The strong force provides the overwhelming bulk of the mass we actually experience by trapping enormous energy inside protons and neutrons. Neither mechanism alone will produce the universe we know. Together they build the rich, structured, material world we inhabit. The next time you pick up something heavy, remember what you've learned tonight. The weight you feel isn't primarily from the Higgs field, even though the Higgs field is essential. The weight you feel is overwhelmingly the energy of the strong force trapped inside the atomic nuclei of whatever you're holding. You're lifting energy, concentrated, confined, packaged into protons and neutrons, but energy. And that energy has been there since those protons formed in the first moments after the Big Bang, over 13.8 billion years ago. The energy inside the protons in your body is older than the Earth, older than the Sun, older than the Milky Way galaxy. It was created in the first microseconds after the Big Bang when the universe cooled enough for quarks to bind into protons and neutrons. And it has persisted ever since, passed from generation to generation, from star to star, from supernova explosions to interstellar clouds to new solar systems to planets to you. You are ancient energy given form. You are quantum fields made flesh. You are the strong force and the Higgs field working together to create something that can stand up, look at the sky, and wonder where its own mass comes from. And now you know, not completely, not perfectly, but better than almost anyone who has ever lived. You understand something about the nature of reality that even the greatest minds in history didn't know until just a few decades ago. That mass is not one thing, that it arises from multiple sources, that the universe is built not from solid, immutable stuff, but from fields and energy and interactions. And the next time someone asks you what the Higgs field is, you can tell them the truth. It's an invisible field that fills all of space and gives certain fundamental particles their inertial mass. It's real. It was confirmed in 2012. It's essential to the structure of the universe, but it's only part of the story. The rest of the story is written in the language of the strong force, of gluons and quarks and binding energy, of Einstein's most famous equation, and of a universe that turns out to be far more strange and far more wonderful than it appears. Thank you for joining me on this journey through one of the deepest questions in science. And remember, the mass you carry with you every day, the weight of your body, the substance of the world around you, it's almost entirely energy. Energy trapped inside protons and neutrons by the strongest force in nature. You are, in the most literal and scientifically precise sense, made of energy. And that's not just a beautiful idea, it's a fact, confirmed by decades of experiments, calculated on supercomputers, and understood through the combined efforts of thousands of physicists across generations. The universe is energy, matter is energy, Mass is energy, and you, standing on this small planet, looking up at the stars, wondering about your place in all of it, you are energy too. Good night.